Hi, my name is Devansh Desai. I'm a senior at UC San Diego, who's majoring in data science, and I'll be presenting this project.
Hi, I'm Advitya. I am a senior data science major at UCSD, and we will be presenting our project on AutoBrick, which is a system to facilitate end-to-end automation of point labels of building sensors and subsystems to be converted to turtle files, which can be utilized by the brick schema. Several commercial buildings today have been subject to various kinds of technological advances to augment human experiences in those buildings. However, different kinds of buildings can have really complicated HVAC systems, different kinds of sensors and subsystems, which would need to be controlled by software, and they would need to, and those buildings would essentially need to, and the software would essentially need to log data in some form. Currently, different kinds of buildings do this data storing process in all of these data-driven applications in different kinds of ways. And there's no uniformity in storing data or in reliably representing all kinds of buildings, objects, and subsystems. This kind of leads to not only non-uniformity in the process of storing data and analyzing data, but also results in a lack of interoperability between the data schemas of different commercial buildings. In fact, according to NIST estimates, the US building industry loses an average of $15.8 billion every single year just due to the lack of such interoperability standards. To mitigate these challenges, the brick schema comes to the rescue here by defining uniform ontology for various kinds of sensors and subsystems and building objects. And brick essentially defines different kinds of ontology and programming for these sensor subsystems and building objects to essentially make commercial buildings into a programming platform. So brick is great, but the biggest hurdle in terms of realizing the advantages of brick and making this a reality for various commercial buildings at scale is this process of brickification, which essentially refers to converting different kinds of schema of different buildings at present to this unified brick schema. As mentioned before, different buildings can have different kinds of complicated HVAC systems and other kinds of sensors and subsystems. To understand the traditional workflow of how data schemas currently are kind of converted to brick, we essentially have a flow chart here where essentially building vendors deal with a basic CSV file. They specify particular kinds of they specify that input to an Excel-like tool, which is called OpenRefine, and they have to essentially do all of the data transformations and pre-processing themselves manually, and also inject an additional API, which is called the reconciliation API, to infer the brick ontology for particular kinds of sensors and subsystems. And then the users have to manually pass the processed data into a tool called Brick Builder, from which they can sort of automate the process of converting that pre-processed data to a turtle file, which essentially sort of defines a relationship between different kinds of building objects and their relationships with each other, which is written in like an RTF-lib kind of, or SparkQL kind of construct, which can then be directly utilized by the brick schema. This process, as you can see here, is highly manual, and it requires a lot of manual intervention in terms of inputs and in terms of stitching particular pieces and various third-party APIs together. To mitigate this, we propose a new workflow, which is called AutoBrick, which essentially deals with this entire process end-to-end and tries to automate and accelerate this process by orders of magnitude. Essentially, now we propose as part of the system that the user can get to specify their own data file and a variety of configurations and auxiliary details related to how they would like this file to be parsed and pre-processed to ultimately be utilized by Brick. And AutoBrick would take in all of the user inputs, infer all of the data transformations that would need to be done, and essentially automates and accelerates this entire brickification process end-to-end by having data transformations and pre-processing which are built into the tool by automatically injecting all the third-party APIs necessary in a reliable sequence to be able to convert the raw CSV files to their brick schemas end-to-end much faster than the traditional workflow without requiring any human intervention within the in between the process. Essentially, AutoBrick boasts three salient features. The first one is declarativity for specifying configurations, which is essentially related to the fact that the users can specify all details about their workload, and AutoBrick is going to execute the entire workload end to end. And hence, AutoBrick also offers orders of magnitude speed and scalability with this entire brickification process, and makes it much more seamless for the user. Essentially, this is how a configuration file looks like. This essentially means that the users can specify a variety of details related to their workload, related to a data file, related to the name of the column where their point labels lie, related to other kinds of details like the delimiters between different elements of a point label, how they would like to actually parse the point label formats, and other kinds of auxiliary details related to additional columns in the dataset, which can potentially help the tool make better predictions about the brick class or about the ontology of specific sensor names and subsystem names. And we have the documentation to support it in the public repository of this tool. Essentially, it's a pretty straightforward set of instruction. The user can simply clone the repository, and they can just set up their environment just by using a simple Python command as displayed here. And it's a simple two-step procedure where they simply have to specify their configurations, and they can literally just run it from their root directory. Yeah, so we have a live demo to also showcase here. So assuming you can see my screen, we have a terminal window open here. If I type a list, I'm essentially in the AutoBrickify directory. And if I go on, the first step after I set up my environment for the very first time is that I need to go to my config folder, and I need to essentially go to the JSON where all of my details are specified. In here, the user has the flexibility to define all of the details that we had mentioned and essentially specify their own kind of action plan on how they would like the tool to deal with specific data files in terms of specific data transformations and inferences that need to be made as part of the brickification process. After all of the changes have been made, after all of the declarations by the user can simply quit out of this configurations file, and the user essentially just needs to run this automation script from the root directory. For the purposes of this tutorial, I'm also going to time this command to really sort of showcase how fast it actually is. So usually it can take a couple of seconds to run as we are talking here, depending on how the file is. Usually in our experience, it has taken from around 8 to 10 seconds. In this case, it actually happens to take 5 seconds. And now, if I try to export the list, we actually got a new turtle file here, which is actually the output turtle file generated from the data file that we had specified. If I go on to loading just for a little bit. Just a second. Yeah, but essentially, if I go on to my output turtle file, you can see that you can essentially see that there are a variety of relationships that can be seen between different kinds of VAVs and between different kinds of point labels and different kinds of building subsystems. And you can essentially see that this is an automatically generated file to encode all different kinds of relationships between different kinds of objects. And you can also see that there are other kinds of auxiliary relationships and details defined here as well. In fact, this turtle file has a lot of other kinds of auxiliary advantages related to the fact that we can even go to this brick viewer tool, and we can in fact upload this file, and the user can also visualize how the schema of this file is going to look like. And as you can see here, we can see that this particular data file that we dealt with only has one particular VAV, which is essentially connected to a variety of different kinds of sensors and different classes of sensors, the names of which have already been inferred by the reconciliation API into the AutoBrick tool, and the user can also interact with these kinds of objects.
So thanks, Nvitya. I'll take it over from here. So this is where the true beauty of our project comes in. So as we said, like there was a lot of manual processing involved in the current state of the art, and the same program that we displayed right now, which took about 5 seconds, but we usually expect it to take around 10 seconds on a normal machine. That same program would have taken 15 minutes if you just followed the previous state of the art. So this is massive. A 90 times speed up is extremely rare to see, and this is where we take pride in like what our project has achieved. Now, one might think that okay, like 15 minutes is not that big, and maybe you just do it once and you forget. But the most important part about this is if you had to do this, like just UCSD alone has almost over 100 buildings, and imagine doing this for the city of San Diego or California or even the United States, and like this 15 minutes to 10-second difference really starts to pile up, and that's why our project is that important and that useful in our opinion. And yeah, Rita, can you get to the next slide, please? So yeah, as you saw, this is what our project does, and now to do this, we had quite a few hurdles to go through. So one major dependency that our project uses is called the reconciliation API, and basically reconciliation API is just an exaggerated dictionary of like what does Johnson controls call something and what does the brick schema call something and so on. So when we started, it was not very accurate. It only worked about 30% of times. So if you had 100 different sensors and equipment in a building, it would only get 30 of it correct. And this was a huge bottleneck for us, as we really struggled to get our code working without getting it to work. So we ended up improving the current state of the art reconciliation API in building our tool, and we benefited both the open source community and also our project. So yeah, basically we had to parse a lot of documentation from Johnson controls, and we ended up improving their reconciliation API. Secondly, we had 41 data sets that we collected off of the UCSD campus, which included a lot of buildings in the engineering department, the Jacob School of Engineering, and so on. And we ended up rectifying all 41 of them. And this is important because this proves that our project is not just a proof of concept that will just sit in a lab and never see the light of the day. We actually were able to like use this and implement it in the real world, and we were able to see results in the real world. And lastly, now this is something a proof of a concept that we are working on since we finished the project ahead of schedule. What we thought about is that not everyone has the skills necessary to write SQL queries, even after generating these turtle files. So what we worked on is called Arena. Now, Arena is a VR environment, which I'm sure most of us should be aware about, where you wear these VR glasses and you're in this virtual world and you can mimic certain things in the virtual world. So, like right now, like this is very simple example, but you have this like Minecraft like space in in your browser, and you can have 3D objects there and so on. And what we are working on is basically a front end for our brick files that is hosted on in Arena, so you can have someone sitting on their sofa in Australia or who has no knowledge of how to write SQL queries, and they could just like push around things and like press buttons in this virtual space, and that our server would translate these taps and touches into actual SQL queries that query the turtle files that were generated by AutoBrick. So we felt that this brings the whole like back end and front end together to like actually push the state of the art further and um, improve the current state of the art, and also make it easier for the layperson who does not know a lot about computer science. So yeah, can you go to the next slide, please? And yeah, so that completes our current work. And as for future work and what we want to do in the future, so right now our process is 99% automatic. It only has one small thing that still needs manual intervention, and it is editing the configuration file for different buildings. So when you saw Vidya open up BIM and uh, look at the delimiter and change the delimiter for the CSV that he was working with, that is something that still needs human intervention, and we want to work on ways to eliminate that need for human intervention. So we are looking into things like regex and more conditional statements to try to capture all of these edge cases. But yeah, the good part is that the default configuration works well for almost 80% of the files. So again, not something that is without which the project is broken. But yeah, this would definitely help us like scale the software much faster. Secondly, we want to add semantic validation to our turtle files. So what I mean by this is, for those familiar with the computer science background, when you write a program, you have a compiler that checks if what you wrote was gibberish or like if it makes sense. And we want to like have the same kind of validation, semantic validation for our turtle fast, to make sure that what AutoBrick is outputting makes sense and it is not complete gibberish that cannot be parsed. And lastly, what we want to do is the virtual environment that I talked about. We actually want to um, have like real world applications on there. Specifically, right now UCSD has a bunch of VAV units, which are just these um, equipment in the HVAC system for different buildings, and a lot of the equipment and sensors fail from time to time. And what we want to do is, instead of having a technician needing to climb up in the ceiling to check these failures, we can have these equipment states mirrored in the virtual environment. So if something turns red, you know for a fact that this equipment is working and you don't need to send a person there anymore. And we think that this will save the university a lot of time, money, and also help with safety for our technicians. And yeah, and can you get to the next slide, please? And yeah, that is about it. So this is the URL to our GitHub project. Thank you so much for coming, and thank you for your attention. If you have any questions, we'd be happy to take it.
Thank you very much for your time.